Alrighty, so we are going to tackle yet another problem involving motion of a charged particle within a magnetic field. But fair warning, this problem is probably one of the harder problems you will see, much harder than last time's. So we are on page 650, problem number 15. For those of you following along at home, we are still in chapter 19, which is magnetism. So I'll read it out loud for you. So consider the mass spectrometer shown schematically in figure here. The electric field between the plates of the velocity sector, this is what they label as the velocity sector right here, and I've drawn the electric field lines as these blue arrows, and those electric field lines are created from a positively charged plate, a negatively charged plate, so of course there will be an electric field between the two. So consider the electric field between the plates of the velocity sector, that is equal to 950 volts per meter, and the magnetic fields in both the velocity sector and the deflection chamber. So this up here is the deflection chamber, and the magnetic field lines are going into the board, from my perspective at least, and so those magnetic field lines are present in the what's called the deflection chamber, which is basically the part that doesn't have the electric field, and it's obviously present within the electric field as I've drawn. So consider those two, and that the strength of the magnetic field is 0.930 teslas, if you're concerned about sig figs. So your goal is to calculate the radius of the path in the system for a singly charged ion with a mass of 2.18 times 10 to the negative 26 kilograms. So the radius of this path, here it's drawn out for you in this dotted line. So here's what's going to happen. And a key of this is that it starts off going straight. So while the proton, it's actually not a proton, it's just an ion. So while the ion is subjected to this electric field, and it's moving at some velocity that we don't know, but we will find out. While it's moving at some velocity in both the electric field and the magnetic field, it experiences no net acceleration. It will stay in a straight line, and so therefore we will eventually figure out that those two are going to cancel out. So the two forces from the electric field and the magnetic field. So the ion is moving straight, and then suddenly it gets out of the electric field section of it, so now it is only being subjected to the magnetic field, and right here it's going to have some velocity that goes up, and then if you do your right hand rule, velocity up going into the page, the acceleration goes left, which is why we see that it will form a circular arc, and then it'll eventually hit this wall over here. And so the goal is to find the radius of that circular arc. So in order to do that, the first thing we want to do is find the velocity right as it exits this chamber. And in order to find the velocity right as it exits this chamber, we need to find the velocity such that the force from the magnetic field cancels out the force of the electric field. So if we draw a free body diagram of our proton right here, it's going to experience an electric field force that pulls it this way. So that's our force electric. And it's going to experience a magnetic force that's pulling it this way. Force magnetic. That's the magnetic field symbol. So that's why I drew it as a beta. So because we know, according to the right-hand rule, that the magnetic force goes left, electric force, as shown, is going to go right, and so they have to equal each other and be opposite and completely cancel out in order for it to continue in a straight line as it does. So because it's in a straight line, we can set these two equal to each other. So the first thing we set is that, the first thing we do is we say that the summation of force on the object is equal to 0. Therefore, the two forces acting on it, the force of the magnetic field, must equal the force from the electric field, just like that. Because those are the only two forces on it, so they must cancel out. So, the force given to it from the magnetic field is given to us by our formula QVB sine theta. I'm not going to write out the sine theta because we already know it's perpendicular, and from our last video we know that that means that sine of theta is going to be 1, so we can ignore that part for now because it is not important. So we have that the charge of the particle times its velocity times the strength of the magnetic field must then be equal to the force electric. And the force electric is given by the electric field, the strength of the electric field, times the charge. That's one of your basic formulas. And you can also get that because volts per meter, if we just do a little unit analysis here, volts per meter We know that the unit of volts is in the units of joules per coulomb. That is one of the definitions of a volt. So joules per coulomb, if we move that to the denominator, we get joules per meter times coulomb. Joules per meter actually is the same thing as a newton. So we get newtons per coulomb. So it makes sense that if our electric field is in the units of newtons per coulomb, in other words, force per charge, that we multiply it by charge to get force. Perfect. So, as you can see, we can actually cancel out our charges here. So for the purpose of finding our initial velocity, the charge doesn't matter, but it will matter later. So we want to find our initial velocity here. So our velocity is equal to the strength of the electric field divided by the strength of the magnetic field, which is equal to 950 divided by 0.93 Teslas. So 950 joules per coulomb or volts per meter, whichever strikes your fancy, and then 0.93 Teslas. That gives us a total velocity of 1021.5 meters per second. So what that means is that this particle must be traveling at exactly, well, we're rounding a little bit, but basically 1021.5 meters per second in order for the magnetic force to be strong enough to cancel out the electric force. That's what's going on. That's why it gets to move in a straight line. So it's going to keep that velocity. It's going to keep the magnitude of the velocity, and then right when it escapes the electric field, right there, that is when it is going to, the electric force is going to drop off, and then it will experience a net force. So then, right at this point, the summation of force on that charged ion is going to be equal to now only the force from the magnetic field. Because earlier we only had the magnetic field force and the electric field force. The electric field force dropped off because now it's no longer between the two charged plates that were creating the electric field. So now it only has the magnetic force. So it is, the summation of force on it is equal to the magnetic force. And we also know that since it's moving in a circular path, we know that it must be experiencing some kind of centripetal force. And this centripetal force is provided by the force of the magnetic field. So what we say is that the force centripetal is equal to the force from the magnetic field. So now our centripetal force, if force is equal to mass times acceleration, and you have to know that the centripetal acceleration is equal to v squared over r, then we know that the centripetal force, if we substitute centripetal acceleration in here, gets us mv squared over r. That's a good relationship to know. So we have that the mass times the velocity squared over the radius, and the radius is what we're looking for, don't forget that that's our goal, is equal to the force afforded by the magnetic field, which we never fully calculated, so we will have to do that, which is equal to QVB, and again we're going to drop the sine theta because it won't matter. QVB, there we go. And actually we will not end up calculating this because velocities cancel out, so if something can cancel out, go ahead and cancel it out. So we're going to rewrite this. Let's get a new color here. We're going to rewrite this as mv over r equals qb. There we go. Now we're going to solve for r, so r equals mv over qb. And if we plug in all of our numbers here, so we are going to plug in, the mass was given to us at the beginning, 2.18 times 10 to the negative 26, 2.18 times 10 to the negative 26. I'm going to have to squeeze this a little bit here. The velocity we are going to borrow from earlier, we're going to throw that right in there, times 1021.5. I might be going off screen a little bit here, but at least I'm narrating so wonderfully. Divided by the charge, 1.6 times 10 to the negative 19 coulombs. If you're not sure where that came from, it said it's a singly charged ion. And so singly charged ion means it's only given one unit of elementary charge, which is the same as the charge on a proton, which is 1.6 times 10 to the negative 19th. And some of you who are observant might notice that I haven't erased that part since last video. Times the strength of the magnetic field, 0.93 Teslas. And that will give you a radius of 1.5 times 10 to the negative 4th meters, or 0.15 millimeters, depending on if you really hate scientific notation. So that is our radius. That is our final answer right here. And so I'm going to walk through all those steps one more time because I know it was a lot. So what we did was we realized that because the object was moving in a straight line, it had no acceleration. And because it had no acceleration, it must have a force that's summed up acting on it that's equal to 0. And so the forces acting on it, the electric field and magnetic field force, must be canceled out. If you want to think about if this particle weren't moving at all, it would only experience an electric force and it would just start accelerating to the right, because if it had no velocity, it would have no force from the magnetic field. So it must have a velocity that is high enough, so that way there is a magnetic force that is strong enough that will overcome the force from the electric field. So we set those two equal to each other and found the required velocity. And interestingly enough, this required velocity has nothing to do with the charge of the particle or the mass. It only had to do with the strength of the magnetic field and the strength of the electric field, which is why in the diagram it's called a velocity selector, because a scientist in a laboratory could adjust the magnetic field strength or the electric field strength to get a certain velocity that he or she wanted. And overall, the goal of this is to actually calculate the mass of an object. So we're doing it a little bit differently because the problem asked us for the radius. But if you wanted to calculate the mass, what they would do is they would actually measure the radius like a normal person, and then from that they could calculate the mass of a particle that you obviously can't weigh because you can't weigh a proton or a single ion. So that's actually what it's used for. So if this object has a larger mass, you can see that the mass is proportional to the radius. Once they find the velocity, the q, and the strength of the magnetic field, or they know those things, then it's just a matter of measuring the radius, and then they can actually determine the mass of objects. So that's what a mass spectrometer really is. It's a device to measure mass, and so that's kind of what we solved for here, except in this case they gave us the mass, and then we had to find the radius that it would travel had it undergone this process. So that was a lot. I hope you learned something. Yeah, magnets are fun. See you next time.